Okay, up until now, we have only looked at one independent variable. In simple linear regression, though we were able to get a significant result, our results may have been misleading. Was class size the only possible variable that could have affected the students' average test scores? We have data collected on other variables in the California schools data set, including the expenditure per student and the percent of students learning the English language. Let's look at the effect of analyzing this question with and without the additional variables. The first thing we need to look into is omitted variable bias. The bias in the OLS estimator that occurs as a result of an omitted factor or variable is called omitted variable bias. Bias in the OLS estimator that occurs as a result of an omitted factor or variable is called omitted variable bias. The two conditions for omitted variable bias are Z is a determinant of Y, an example Z is part of U, the error term, and Z is correlated with the regressor X, an example correlation of Z and X does not equal 0. Both conditions must hold for the omission of Z to result in omitted variable bias. In the test score example, English language ability, whether the student has English as a second language, plausibility affects standard test scores. Z is a determinant of Y. Immigrant communities tend to be less affluent and thus have smaller school budgets and higher student-to-teacher ratios, so Z is correlated with X. Accordingly, beta 1 is biased, but what is the direction of that bias? What does common sense suggest? If common sense fails you, then there is a formula. Our point estimate for beta 1, if we add the standard deviation of the mean of the population divided by the standard deviation of the sample mean, or the standard deviation of the error term divided by the standard deviation of X, then we multiply it by the parameter correlation rho. The result of this will tell us the direction of the bias, if it's positive or negative. If we are lucky, it will be 0, which means there is no omitted variable bias. We have distinguished between two uses of regression, for prediction and to estimate causal effects. Regression also can be used simply to summarize the data without attaching any meaning to the coefficients, or for any other purpose, but we won't focus on that use. In our test scores example, we can check to see if there is a bias in our estimator. So even if our sample is large, our estimator beta 1 will not be close to the population parameter of beta 1. In the class size application, we clearly are interested in a causal effect. What do we expect to happen to test scores if the superintendent reduces the class size? Causality is a complex concept. We will take a practical approach to defining causality. Causal effect is defined to be the effect measured in an ideal randomized controlled experiment. Ideal, as subjects are all follow the treatment protocol. Perfect, compliance, no errors in reporting, etc. Randomized, subjects from the population of interest are randomly assigned to a treatment or control group, so there are no confounding factors. Controlled, having a control group permits measuring the differential effect of the treatment. And experiment, the treatment is assigned as part of the experiment. The subjects have no choice, so there is no reverse causality in which subjects choose the treatment they think will work best. So back to class size. Imagine an ideal randomized controlled experiment for measuring the effect on test score of reducing student-to-teacher ratio. In that experiment, students would be randomly assigned to classes which would have different sizes. Because they are randomly assigned, all student characteristics, and thus our error term, would be distributed independently of student-to-teacher ratio. Thus, the expectation of our error term given our student-to-teacher ratio would be 0. That is, our least squares assumption number 1 holds in a randomized control experiment. How does our observational data differ from this ideal? Well, the treatment is not randomly assigned. Consider the percent of English learners in the district. It plausibly satisfies the two criteria for omitted variable bias, where z equals the percent of English learners is a determinant of y, and correlated with our regressor x. Thus, the control and treatment groups differ in a systematic way. So the correlation between student-to-teacher ratio and percent of English learners does not equal 0. Randomization implies that any differences between the treatment and control groups are random, not systematically related to the treatment. We can eliminate the difference in percent of English learners between the large class, control, and small class, treatment, groups given by examining the effect of class size among districts with the same percent EL, or English learners. If the only systematic difference between the large and small class size groups is in the percent of English learners, then we are back to the randomized controlled experiment. Within each percent of English learners group, there is one way to control for the effect of percent of English learners when estimating the effect on student-to-teacher ratio. Okay, let's return to omitted variable bias real quick to lead our discussion. There are 3 ways we can overcome omitted variable bias. Run a randomized controlled experiment in which treatment, student-to-teacher ratio, is randomly assigned. Then, percent of English learners is still a determinate test score, but percent of English learners is uncorrelated with student-to-teacher ratio. This solution to omitted variable bias is rarely feasible. We can adopt the cross-tabulation approach with finer gradations of student-to-teacher ratio and percent of English learners. Within each group, all classes have the same percent of English learners, so we control for percent of English learners. Soon, you will run out of data. And what about other determinants like family income and parental education? We can use a regression in which the omitted variable percent of English learners is no longer omitted, so we just include that as an additional regressor in multiple regression. So now we can finally talk about multiple regression. So multiple regression is very similar to linear regression, except we have more than one independent variable. It also changes how we can interpret the slope value of beta 1. Beta 1 equals the effect on y of a change in x1 holding x2 constant. Likewise, beta 2 is the effect on y of a change in x2 holding x1 constant. This down here. So this kind of summarizes what I just said in the last slide. We're looking at beta 1. We want to see the change in y divided by the change in x1 holding x2 constant. And for beta 2, we want to see the change in y divided by the change in x2 holding x1 constant. And beta 0 is, or the intercept, is the predicted value of y when x1, x2 equals 0. The OLS estimator minimizes the average squared difference between the actual values of y and the prediction or predicted value based on the estimated regression line. You have to use calculus to solve this, and thus we use software to get the values for our intercept and beta estimators. Let's look at an example from the California schools data. Our first model looked at the effect of student-to-teacher ratio on average test scores. We found that for every added student, we decrease our average test scores by 2.28. Now, let's see what happens when we add in the next variable, percent of English learners. We see that now the student-to-teacher ratio has a decreased effect. Now, adding another student to the class only decreases the average test score by 1.10. We also see that the percent of English learners decreases the average test score by 0.65. So that is just what our regression equation looks like. If we use R to run our regression, we will get this output. Some things to notice are the R squared and adjusted R squared. The adjusted R squared takes into effect the addition of independent variables. So we explain a slightly less amount of variance in average test scores with the addition of the second variable. Our p-value for the model is significant, so it's still a good model. We can see at the bottom that both our coefficients are statistically significant and that student-to-teacher ratio has a higher effect than percent of English learners on average test scores. There are several measures of fit that we are still interested in. R squared is the fraction of variance explained in y by x. However, this measure of fit is only useful if there is only one x. If we have more than one x, then we have to account for the other independent variables. Hence, we use the adjusted R squared, which adjusts for each parameter we are estimating. We will go over how to do that in a moment. The other two measures of fit we are interested in are the standard error of regression, which corrects for the number of degrees of freedom, or the root mean square error of approximation, or RMSE, which does not account for the number of degrees of freedom. Both the standard error of regression and RMSE measure the variability of y around the regression line. The smaller these values are, the better claims we can make about our dependent variable y. The major difference between these two equations is the correction for the degrees of freedom. In the standard error of regression formula, we use the n minus k minus 1, which is how we correct for the degrees of freedom, where n is sample size and k is the number of independent variables in our regression. The R squared value represents the amount of variation in y that can be explained by our independent variable. It is found by dividing the estimated sum of squares by the total sum of squares. Or we can divide the sum of squares residual by the total sum of squares and then subtract that from 1. Either way will give us the R squared value. To find the estimated sum of squares, we want to know the difference between our point estimated for y and the average of those estimated y's. This is easy to remember because both are estimates of y hat. The total sum of squares is the actual value of y from the mean of y. Both of these values come from the data and not what we are estimating with the regression. The last note is that every time we add a term, the R squared value will go up. This makes sense because we are explaining more of the estimated variance and thus decreasing the residual error. However, this does not take into account that some variables may have overlap in the variance they are explaining. Thus, R squared is overestimated. To solve this problem, we must account for the number of parameters we are estimating. So to adjust the R squared, we create the adjustment term of n minus 1 divided by n minus k minus 1. Now we account for the sample size and the number of free parameters that we are estimating. N equals sample size and k equals the number of x variables in our regression. If we look at an example, the average test score is regressed by the student-to-teacher ratio. Student-to-teacher ratio's coefficient is negative 2.28, meaning that every added student will decrease the average test scores by 2.28. The R squared is 0.05, which is pretty low, so we are not actually explaining very much of the variance in the average test scores. Well, let's look at another variable. We add in the percent of English learners into the regression. This decreases the effect of student-to-teacher ratio on the average test scores to 1.10. Also, we drastically increase our R squared value to 0.426. Now we are able to explain a lot more variance in our average test scores. The adjusted R squared and R squared values are very close at 0.426 and 0.424. This is because there is not much overlap between our two independent variables. Overall, we have learned that a lot more of the variance can be explained with the percent of English variable than the student-to-teacher ratio variable. There are several assumptions that are important to use inference in multiple regression. We're going to focus on these four: that the conditional distribution of our error term given that the independent variables have a mean of 0. Variables are independent and identically distributed, and there are no large outliers, and there is no perfect multicollinearity. The first assumption, this has the same interpretation as in regression with a single regressor. Failure of this condition leads to omitted variable bias. Specifically, if an omitted variable belongs in the equation, so the error term, and is uncorrelated or is correlated with an included x, then this condition fails and there is an omitted variable bias. The best solution, if possible, is to include the omitted variable in the regression. The second related solution is to include a variable that controls for the omitted variable, discussed shortly. Assumption number 2, that the x's are independently identically distributed. This is satisfied automatically if the data are collected by simple random sampling. Assumption number 3, large outliers are rare. This is the same assumption as we had before for a single regressor. As in this case of a single regressor, OLS can be sensitive to large outliers, so you need to check your data and use scatter plots to make sure there are no crazy values or typos or coding errors that might have caused for an outlier. The fourth assumption is no perfect multicollinearity. Let's look at a possible example of how this might occur. Let's say we accidentally added the student-to-teacher ratio to our regression twice, as we did here. Software would automatically drop the second and just run it as simple linear regression. Other possibilities for perfect multicollinearity is if we try to regress using a constant, like create a dummy variable that is a constant and applying to above and below 20 students. If we add a constant to our regression or excluded when we would have an example of the dummy variable trap. Suppose you have a set of multiple binary dummy variables, which are mutually exclusive and exhaustive. That is, there are multiple categories and every observation falls in one and only one category. If you include all these dummy variables and a constant, you will have perfect multicollinearity. This is sometimes called the dummy variable trap. You can solve the dummy variable trap by omitting one of the groups or omitting the intercept. Perfect multicollinearity usually reflects a mistake in the definitions of the regressors or an oddity in the data. If you have perfect multicollinearity, your statistical software will let you know, either by crashing or giving an error message or by dropping one of the variables arbitrarily. The solution to perfect multicollinearity is to modify your list of regressors so that you no longer have perfect multicollinearity.